All right, Chapter 12, Section 1, Goodness of Fit Test. Okay, this test is testing to see how well something fits a distribution that we've already determined. So that's what it's about. So some things we need to know. It's an inferential procedure used to determine whether a frequency distribution follows a claimed distribution. So this is like when M&M says that or let's do Skittles. Skittles says that every bag of Skittles should have approximately 25% of each color. Because there are 4 colors, so everyone should be the same. Well, does it or doesn't it? We should check a bag of Skittles to find out. However, I don't have bags of Skittles to send you, so we're just going to have to do the math here. And if we had time, we would do the Skittles scenario at school. Okay, chi-square distribution is not symmetric. As you can see, the shape is very similar to some of the others we've already looked at. Depends on degrees of freedom. Each one is different. As the number of degrees of freedom increases, it becomes more symmetric. And remember that chi-squared is never negative. It's always greater than or equal to 0. Just a real quick review on chi-squared. Again, we're checking to see if a distribution matches. So the first thing we have to figure out is that there are 2 terms we're going to work with, and one of them is expected and the other is observed, and we'll talk about the formula and all that stuff as we go. So first of all, expected value is n times p for every outcome, the number in the sample times the probability of that thing happening. So I have an example. Marketing specialist claims that among supermarket shoppers who prefer a particular day, these rates apply. 7% prefer Sunday, 5 Monday, 9 Tuesday, 11 Wednesday, 19 Thursday, 24 Friday, and 25% prefer on Saturday. If 1,500 shoppers are chosen at random, how many should shop each day? So we're going to make a little chart here. We have Sunday, Monday, Tuesday, Wednesday, we'll just go over here, Thursday, Friday, and Saturday. Okay, so we have those. And we can see from the problem that we ask 1,500 people to shop, and we have these percentages. So if 5% prefer to shop, 7% prefer to shop on Sunday, 1,500 times 0.07 tells me that 105 would shop on Sunday. This is now my expected value. So on Monday, 5%, 1,500 times 0.05 is 75. Let's see, 9%, so 1,500 times 0.09 is 135, 1,500 times 0.11 is 165. Thursday is 19%, 0.19 times 1,500, 285. Friday is 24%, so 0.24 times 1,500 is 360, and 25% prefer Saturday, so 0.25 times 1,500 gives me 375. That is how many people I would expect to shop on those days out of the 1,500 shoppers that have a particular day that they're partial to. All right, I'm going to adjust this a little bit more. There we go. Okay, and it's just simple. Take the percentage times the number in the sample. Our sample is 1,500, so n times p, and each of the percentages is different. This becomes our distribution. That's what we're going to compare to. So let's take a look at our next one. And everybody does this part the same way. Okay, so H sub O says that P of A equals P of B is P of C is P of D. They're all 1/4. That's my H sub O. They're all equal. They all follow this distribution. So the H sub 1 is, at least one of them is different. And we want to test this claim at alpha is 0.05 level. So if you are a TI 84 or higher, if you have a TI 83, I'll get to you in just a minute, so hold tight. Okay. Both of you can start the same. Yes, both of you can start the same. So TI-81 or TI-83 and TI-84. It doesn't matter. Everybody starts the same. Input your data into your lists. So list 1 is going to be observed, L1. L2 is going to be expected. Okay, so everybody put list 1 and list 2 in. List 1 is 30, 20, 28, and 22. List 2 is 25, 25, 25, 25. I think I already have that. Did you? Okay. So my list 1 and list 2. So step 1, enter L1 and L2. Everybody does that. Okay. So now, for the 84 users, hit Stat, Tests. We're going to go all the way down here to chi-squared goodness of fit. So number 2, you're going to go to chi-squared GOF test. You're going to enter. It says observed is in list 1, expected is in list 2. You have 1, 2, 3, 4, so degrees of freedom, you have to enter the D of F. So you've got n minus 1 for D of F, and you have 4 items, so 3, and choose calculate. And it tells you your chi-squared value is 2.72, and your p-value is 0.4368. If you were going to compare that to your alpha, alpha is 0.05, 0.4368 is greater than 0.05, we would fail to reject. Okay, so pause there for a minute for those of you. 83 users, you're right there, so it's really not hard. You already have list 1 and list 2 in. Okay, now you have to do a little extra. So go to list 3. So up on list 3, you want to type this. So for L3, way up at the top, you're going to type this. L1 minus L2 squared divided by L2. So it's going to look like this. Parenthesis L1 minus L2, close the parenthesis and square it, divided by L2. And hit enter. It puts the values in for you, and then enter. Okay, you're good so far. Now you have to do one variable stats. So stat calc, one variable stats. You want it on list 3, and you're going to calculate. And you're going to look for this. The sum of the x's is 2.72. Oh my goodness, look at that. That's your chi-squared value. The sum of the x's is your 2.72. All right. Now, to get your p-value, your step 4, you're going to do catalog. Okay, so second catalog. You're going to scroll all the way down till we get to the chi-squared ones. You want chi-squared CDF parenthesis. Okay, so once you get to there, hit enter, and you're going to type this in this way. You're going to do your chi-squared value followed by 1 times 10 to the 99th, comma, and your degrees of freedom. That's the syntax. So in our case, that's going to look like this. 2.72, comma, 1 times 10 to the 99th, comma, 3. 2.72, comma, 1 times 10 to the 99th. Make sure you arrow over so you get drop back down, comma, 3. Close your parenthesis, and you have your p-value, 0.4368. Look at that, it matched up. Same result, 4368 is greater than 0.05, therefore you would fail to reject. The same as before. Yes, a couple of extra steps, but you will get there just the same. Let's try that again. This scenario is a little bit different. They don't give us the expected, so we have to figure it out. And the clue to this is in the problem. The researcher wanted to determine whether pedestrian deaths were uniformly distributed over the days of the week. Randomly selects 300 pedestrian deaths, recorded the day of the week in which the deaths occurred, and obtained the following results. So we need to calculate expected. Well, they're all going to be the same. They're all going to be 300 divided by 7. Because 1/7, because there are 7 days of the week. So that's what we're going to do. So go to Stat, Edit. We're going to put our information in List 1. So 39, 40, 30, 40, 41, 49, 61. And in List 2, I'm just going to type it as a fraction. 300 divided by 7. 300 divided by 7. Oops. 300 divided by 7. 300 divided by 7. Oops. Again, I hit it again. 300 divided by 7. 300 divided by 7. And 300 divided by 7. So I have all those in. Okay, so now, okay, TI-84 people, go ahead, you're doing the G of F test. My 83s, while I'm here, I'm going to go ahead and type in my formula, and that is parenthesis L1, I guess I should put this over here, minus L2, closed squared, divided by L2, enter. It puts those values in. I'm going to do second, I'm sorry, I don't want to do second, stat, calc, one variable stats, from list 3, which gives me my sum, which should be 13.227, which if I do the G of F test, get down there, there it is. List 1, list 2, my G of, my goodness, 6 this time, and calculate. Oh, look at that. 13.227. Very good. So chi-squared is 13.227. My p-value should be 0.03957. So I'm going to go over here and do that. So again, I do second catalog all the way down to CDF. Chi-squared CDF. There it is. I put in my number 13.227, comma 1 times 10 to the 99th, arrow over so I can drop back down, comma, my degrees of freedom is 6, close it out, and I get 0.0395. Look at that. 0.03957 is my p-value in both cases. I'm comparing that. Oh, and alpha, by the way, was 0.05. I didn't tell you that. I should have. So I'm comparing 0.0395 to 0.05. It is less than, so we would reject the null hypothesis. So we are saying that it's not uniformly distributed, even though it appeared to be when we started writing the numbers down. They're really relatively close. But again, this, I think Saturday kind of threw them off. So if you have a TI-83, you have to do a few extra steps. If you have a TI-84, it does all that math for you. Not too difficult, but I think you can handle it. And that is how we do chi-squared goodness of fit.